Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to lecture 19 of basic electrical circuits. In the previous lecture we were looking at how to calculate responses to a step of a first order circuit, which could be an RC circuit or an RL circuit. In this lecture what we will do is we will look at what to do for a second order circuit, that is second order RLC circuit. At the end of the previous lecture we considered two second order circuits and then wrote down the differential equations for them. In this lecture we will start from that point and calculate the responses and different parts of the response, just like we did for the first order circuits. Okay. And as I said, we considered two circuits. And I will assume that we are interested in the capacitor voltage Vc. Okay. Now, this is not necessarily always the case. It could be that I am interested in the current or the voltage across the resistance. I can write down the differential equation in terms of any variable. Now, I could write it in terms of Vc, I could write it in terms of IL or VR or anything else. Okay. Now, if I write it in terms of Vc, I will get LC times second derivative of Vc plus RC first derivative of Vc plus Vc equals Vs. Okay. Now, the same thing could be written in terms of some other variable. Let us say we choose to write it in terms of the inductor current. Okay. Now, it turns out I will not show it here, but even if we write it in terms of the inductor current, we would get the left hand side of the differential equation to be exactly the same. That is, what I mean is, here with Vc as variable, we will have Lc second derivative plus Rc times first derivative plus Vc equals something dependent on the input Vs. Okay. That is my convention. I always put the independent source on the right hand side. If I choose to write it in terms of IL, okay, then I will get exactly the same Lc second derivative of IL plus Rc first derivative of IL plus IL equals, this will be some other function of Vs. Okay. So, I am not going to find that here, but the point is, if you take a given circuit and then identify any variable and write the differential equation for it, the left hand side will remain the same. Okay. Meaning the differential equation, the left hand side part or the homogeneous part of the differential equation will remain exactly the same. Is this okay? Any questions about this? Now, let me write it in terms of write it for a different second order circuit, which is Okay. I have an input Vs and I have not looked at what kind of input it is. So, the differential equation we have written is quite general. Then depending on the type of input, whether it is a step or a sinusoid, we can go and do analysis further. Again, I identify this Vc as variable. I believe that is what I did last time as well. Okay. In that case, I will get LC second derivative of Vc plus L by R first derivative of Vc plus Vc equals L by R first derivative of Vs. Okay. Now, again I can take some other quantity as variable. Instead of Vc, I will take there appears to be some problem with this. Let me fix that. Okay. So, I think we are back in action. So, if I choose some other quantity as a variable, let us say the inductor current IL, again as before I will get the same equation on the left hand side. Okay. And on the right hand side I will get some other function of Vs. Okay. Now, you see also that for this particular circuit and this particular circuit, the left hand side looks different. That is, the middle term for instance is RC times first derivative in the left side case and L by R times the first derivative in the right side case. Okay. Now, these are two sort of standard types of second order LC circuits. Okay. Now, we will do many things with the solution. We will see how to solve this for these things for step response, etc. And those will be general for any second order circuit. In fact, they do not even have to be LC circuits. Now, in this particular case, we have chosen two different LC circuits and they will have slightly different types of responses. Okay. Now, what is the difference between these two? I would like answers from the participants. What is the difference between these two circuits? Yeah, so there was an answer from Vikas that the first one is a series RLC and the second one is series parallel, but it is actually parallel RLC. What I mean by this is the following. Okay. with a nulled circuit, that is, you null the independent source, that means that in this case we have only an independent voltage source. Okay. So, we set Vs equal to 0. If we had a circuit with current sources, we would also set that to be equal to 0. Okay. So, once we null this, what we get is R, L and C. Okay. We get a single loop of RLC in series for the circuit on the left side. And for the circuit on the right side, if you null this, we will see RLC in parallel. Okay. Now, I have drawn the R like this, but it is very clear that R and L and C are in parallel with each other. Okay. So, we get only two nodes with RLC in parallel with each other. Okay. So, basically by looking at the nulled circuit, we can tell whether it is a series RLC. So, the circuit on the right side is known as, the circuit on the left side is known as a series RLC circuit, and the circuit on the right side is known as a parallel RLC circuit. Okay. Now, it depends on basically the nulled circuit. Okay. So, now it does not matter where the source is. For instance, what I mean is, so let us say I had a circuit like this. Or a circuit like this. If you null the source Is, these two look different from each other, but when you null the source, you will simply get R, L and C in series. Okay. So, these are basically series RLC circuits. Similarly, even in this case, I could have sources in different places, voltage sources in series with one of these branches, or current source in parallel with something else. Okay. In all of those cases, I will get R, L and C in parallel. If I do get that, it is a parallel RLC circuit. Okay. So, there is a question on previously recorded videos. I believe they should be online, but after this lecture I will go and check. If it is not online, I will ask them to have it put up online as soon as possible. Okay. So, the idea is to have every lecture online before the next lecture. Okay. So, now I showed that this is the differential equation governing this circuit, this is the differential equation governing that circuit, but in general if you have a series RLC circuit, you will get a differential equation of the form LC second derivative of Vc. Like I said, This could be any other quantity, you will get the same thing. Okay, the difference will be in the right hand side. Okay. Now, like I said, you could have the input as a voltage source or a current source or something else. As long as the null circuit reduces to this, the left hand side of the equation will be of this form for any variable. Similarly, if the null circuit reduces to a parallel RLC circuit, the left hand side of the differential equation will be of the form LC second derivative of the variable. I am taking Vc as an example, but as I keep emphasizing, it could be any other variable. L by R first derivative plus Vc equals, this will be related to the independent source, okay, in some way. Okay. So, once you are able to set up the left hand side, the transient response or the natural response can be determined, okay, because for instance you can set the right hand side to 0 and that gives you a natural response with 0 input, right, that is the 0 input response, which is also the natural response for 0 input. Okay. Obviously, with 0 input there is no force response. Force response is something that is proportional to the input. With 0 input, the force response will be 0. Okay. Any questions about this? I classified the second order RLC circuit into two types, but the method of solving the second order circuit will be the same even if it is not RLC. Okay. Now, RLC is an important practical case. So, I have classified them into two types, where one has series RLC in a single loop, the other has R, L and C in parallel with each other. If you have series RLC in a single loop, the differential equation will be of this form, where right hand side could be anything. If you have R, L and C in parallel, the differential equation will be of this form and the right hand side could be anything. Okay. Any questions? Now, there is a question asking, is it possible to calculate the time constant? Now, we will do that. A first order circuit has a single time constant and a second order circuit will have two time constants. In general, an nth order circuit will have n time constants. Okay. So, we can calculate that. Now, it turns out that for higher order circuits, that is order higher than 1, you can mention the time constants, you can specify the time constants, or you can specify alternatively the characteristic frequencies. Okay. Frequently, that is what is done. So, we will look at that. Okay. So, if you recall, let us go back to the first order circuit. This is again an example RC, but it could be any first order circuit. The differential equation governing this with Vc as variable was RC dVc dt plus Vc equals Vs, and we could write down Vc for a step input if Vs is a step input that goes from 0 to Vp. Okay. I could write Vc as Vp times 1 minus exponential minus t by RC, okay, plus the initial condition exponential minus t by RC. This we have done before. okay, and we call this the 0 state response, and this is the 0 input response, okay. And this can also be rewritten as Vp plus Vc of 0 minus Vp exponential minus T by Rc. This is specifically for a step input or a constant input, okay. When I say a step, it is really a piecewise constant input. And we call this the steady state response, and this the transient response. Alternatively, this is also called the forced response, or this is called the natural response, okay. Now, for the second order circuit also, we will calculate these things, that is the steady state response or the forced response, and the transient response or the natural response, okay. And at every step, I will try to make an analogy with the first order case, so that you can associate the results and understand the results clearly, okay. Because I will not be deriving formally the solution to the second order differential equation. I will give you the solution and say how it is similar to what we have in the first order case. There is a question asking what is the transient response and natural response, okay. The transient response and natural response are the same thing, okay. They are just two different names for the same thing. Now, if you look at the total response, there will be a part in the first order case containing exponential minus T by Rc, okay. Now, this exponential minus T by Rc is the natural response of the first order circuit. So, the part that contains this is the transient response or the natural response, okay. Now, in a more complicated circuit, there will be what are known as natural modes of the circuit, okay, which will be of similar form, exponential minus T by something related to the circuit. So, the parts of the response that contain those things are known as transient response or natural response, and this part which depends only on the input, okay, which depends on the input is known as the steady state response, okay. Is this clear? Basically, for a first order case, whatever contains exponential of minus t by the time constant of the circuit is the natural response. This is okay? So, now first thing we observe is that for a first order circuit, the steady state response or the forced response is a constant for a constant input, okay. What I mean is the input changes from 0 to Vp, that is input is basically Vp after t equal to 0, okay. That gives a steady state response which is Vp, okay, which is also a constant, Now, it happens to be the same as this, but in general it will be some constant. And you would have seen earlier that this was true for any constant input case. We discussed the step response of first order circuits extensively. We calculated the steady state response by open circuiting all the capacitors. So, if you have a constant input, the output will also be some constant. Okay. So, this is the first thing that we will use, and it turns out that exactly the same thing is true for second order circuits also. Okay. So, let me first take the series RLC case. And let me now consider this going from 0 to Vp. Okay. I have RL and C, and I am looking at Vc. So, Vc of t will be of the form steady state response plus transient or forced response plus natural response. Okay. So, just like for a first order circuit, for a constant input, here you have to understand what is meant by constant. The input changes from 0 to another constant. So, I am looking at what happens after t equal to 0, and that is a constant input. The steady state response is also a constant. Okay. Now, I would like answers from the participants. What is the steady state response of this circuit? Now, we have not evaluated the response in detail, but please look at the circuit and think about it. The input is a constant at Vp for t greater than 0. The steady state response, I mean what happens after a very long time, and all the quantities are constants. What will be the value of Vc? What is the steady state value of Vc?